can now delve into what we would class as special geometry applications and start to produce parts because of the technology and the software behind it. But there's still a specialism within that product range that the people who may produce them don't necessarily have a full understanding of.
Welcome to the MTD podcast. My name is Rowan Robinson. I'm a proud member of the MTD team. Now today we're going to be talking with three illustrious Hexagon colleagues who are here with me today. But we're going to be talking about what I find quite a fascinating topic is the proliferation of EV, electric vehicles in kind of the marketplace, but how they differ and what similarities are between kind of general combustion engine vehicles as well. And the challenges that manufacturers face in making these electric vehicles and developing them, and how Hexagon production software can help with the manufacture of these types of vehicles. But first, I'm going to introduce the people, the panel today. So I've got Gareth to my left here. Gareth, could you please introduce yourself?
Hello, my name's Gareth Hemwood. I work for the production software division. I look after the metal cutting cam products and also the MRP products for Hexagon production software. My background, I'm a time-served engineer. I did a toolmaking apprenticeship and then have worked my way up through CNC engineering manager, production manager.
Brilliant.
Hexagon.
So when we talk about how you actually make the cars, we'll be going straight to Gareth, right? We'll forget everyone else. Gareth can do it. Brilliant. And then I've got Ollie as well. Ollie, could you please introduce yourself?
Yeah, so hello, my name's Ollie Noakes and my job title is project engineer. So I work for the metrology side of the business. Now, I've been with Hexagon for 8 years, and over that time, my focus has been very focused around the automotive industries, particularly the powertrain aspects of what we do. So we're heavily involved with lots of the powertrain gearbox assembly metrology, where we use our UHAR product line, the ultra accuracy product line, for that ultimate accuracy within the production environment. So we focus on not just measuring the parts, but the whole metrology solution that sits behind that and how we integrate it as part of the full system, both with D&E and with production software. Who's sitting to my left and my right.
Absolutely. So when you make the part, when Gareth made the part, then it's obviously really important to inspect it as well. And there's a lot of interesting problems around the production of electric vehicles that we're going to hopefully discuss today. But moving on to last but not least is Reese. What do you do, Reese?
Oh, yeah, well, hi. Yeah, so I work within the design and engineering, D&E part of Hexagon, which really covers the computer-aided engineering side of the business. And specifically, I work in a group called System Dynamics, which includes Romax software, which is a speciality of mine, which is the system-level analysis of transmissions and rotating machinery. So, yeah, the gearboxes that you'd normally see in an EV transmission. And yeah, I've been working in the industry for about 15 years, various roles. I even have a PhD in the analysis of gearboxes. So
oh my god, so we've got a veritable genius in our midst. I'm afraid I'm shaking my boots.
Yeah.
I'm very looking forward to what you're ready to tell us today, Reese. But first of all, I think I'll open up with kind of a simple question for those who have been living under a rock who are listening to this. What is an electric vehicle? Ollie, how about you? What would you take on? Is it hybrid? Is it just pure electric? What constitutes an electric vehicle?
So I think there's two sides to it. There's the current hybrid technology moving into the full electric, but again the focus that we see is all of the components that go into that. We're trying to look at what is the same, what can we take that is the same as the combustion engines we've had to date, the combustion engine car we've had to date, and what of the EV sector is new that requires us to look at applications differently and come up with new ways to solve the problems that we see in the industry.
Absolutely. And what I find fascinating actually is the combustion engine has been around for almost 100 years now. And it's been kind of optimized to the nth degree where actually they're really bloody efficient, if I can say that word. And so it's probably going to take a lot of effort to knock that off its pedestal. But Gareth, why are we moving now to electric vehicles over a combustion engine, please?
Yeah, I think we're moving over it for more sustainability, better for the environment.
No, that's absolutely fine. Yeah, so we're moving to the electric vehicles because oil might be running out, and there's definite environmental consequences to continuing with combustion engines. Let's first of all discuss what the similarities are in the challenges faced by making a car is very hard. But what are the similarities that manufacturers can bring their knowledge over from making combustion engines over to making a standard electric vehicle?
So again, with standard combustion cars to electric vehicles, there's still a lot of the components are the same. You know, you still have the suspension parts, the bearings, the wheels, the body panels, the plastic parts as well. So these are still being used today as conventional. And again, we're just trying to streamline the processes and make them more efficient and reduce material waste to cut down costs as well.
Absolutely. And Hexagon offer a lot of software packages that deal with kind of mold and die solutions. How does Hexagon help with producing kind of body panels, with producing plastic parts, cosmetic parts, and how do you try and help optimize those processes as well?
So again, with the plastic parts and the body panels, we've got Visi, which is our mold and die product. So again, we can do full press tool design. Again, we can reverse engineer that back from this is the initial component, and then we can build the tools around it going backwards. Again, we can simulate that process for the press tools. And again, we do the same for the injection molding part. So again, we can take a finished component, build a tool and a mold, separate it, put the runners in, the cooling channels, do full simulation, and again, we have a link to a flow analysis software. So at least we can simulate the process to make sure that there's what you're producing is actually going to mold correctly.
Absolutely. And the people who listen to this who might be listening to this in the car right now, they look at your steering wheel, you've got plastic cover on the front of the steering wheel. You might think, oh, it's easy to make, but actually the molds and the dies that are required to make these components are very complicated.
Yeah, there's just to make a small part, the tool is actually very large. So again, the bigger the part, the tooling is massive, and again, they need big injection molding presses to actually press the parts.
Absolutely, you need a lot of smart software to help generate even just the tool paths to make those kinds of mold and dies. But let's move over to you, Reese, or even actually Ollie as well. I think you guys have got a lot of knowledge in this space. What are the differences in components between EV and combustion? There's a lot of differences as well as the similarities that come because of cosmetic.
Yeah, so, I mean, let's talk about the elephant in the room, maybe, or I should more likely say the elephant at the bottom of your car or your EV, which is this huge battery pack, which is sort of more seen in electric cars. Whereas before you might have a fuel tank which had maybe 60 litres, so you're talking about 60 kilograms of fuel if you had a full tank in the back of your car. Now we're talking about full, hundreds of kilos worth of batteries that sit at the bottom, and that has a big impact from a simulation point of view in terms of the ride and handling characteristics of your vehicle, carrying that weight so low down in the car. But then you also got, and obviously within Hexagon we can analyse that using Adam's car, which is a tool that we use to simulate the performance of the car using a multi-body dynamic simulation. And then also you've got the fact that, again, this battery pack is exceptionally rigid. It's very stiff underneath there. So the behaviour of this electric vehicle under a crash scenario, so if you imagine having a side impact in a car, before with an electric vehicle, when you don't have this big component at the bottom, that car would have a crumple zone that would protect the passengers within it and absorb that impact. Whereas now we've got this very rigid battery there that stops you from being able to do that. So again, it's being able to understand how that impact could impact the safety of your passengers. And again, using something like Dytran, which is part of the MSC software portfolio, which is part of Hexagon, you can undertake these sort of crash simulations before you've even got to the fact where you're talking to Gareth and manufacturing these components as well.
Absolutely, yeah. and safety is obviously one of probably the most important characteristic in designing a new product that thousands, if not hundreds of thousands of people are going to be using, especially in a car that goes quite fast, so the dangers are significant if the safety is not quite there. But how important is it to simulate the safety aspects of the car compared to, I mean, the costs associated with designing and making a prototype and then physically crash testing that?
Absolutely. I mean, yeah, you're talking about the cost of making a complete car just to crash it into a bollard within to understand the performance versus spending a few hours a day running the simulation, and then also using that information to make design changes and make sure that when you put it through those tests, you are you're as close to guaranteed a successful impact there. So and again, we talk about the EVs being relatively new. I mean, let's be fair. I think an electric vehicle was invented before an internal combustion engine car.
Yeah, they've been around for a long time, actually.
But now they're becoming more mainstream, and there is a real race for EV manufacturers to grasp a share of this ever-growing market. And so it's again, from a time point of view, simulating up front increases the speed to market and gives them better opportunity to capture some of that market share.
Absolutely. Like you say, it's not quite a new product. The first one was like a little personal car, wasn't it?
Yes.
It was like a lead acid battery, which is horrendously weighty. But enough about the personal cars. Like you say, it's really important when you're designing a brand new product that you need to do as much as possible in the initial phase, because that's when the ability to change things is the highest and the cost of change is the lowest. And that's where the software is really important in trying to design these new pieces of software. But let's move on to let's imagine you've kind of made your prototype EV car, Ollie. What are the challenges associated with inspecting the components? Because there's a lot of very different components in an electric vehicle compared to a combustion engine. What are those different components and how do they need to be inspected differently?
So yeah, I think we need to start at the beginning and first work out what we can take from what we already do and what we need to look at that's new. So if we take an example of an application at the moment where we see lots of people who are after a way to validate parts, we take the hairpins that are part of the stator assembly that actually generate the power in the motor. So bent copper is ultimately what this is, and the process to actually produce them is quick. So it's effectively extruded and bent. And
so by hairpin, we're just imagining kind of a copper wire, almost.
Yeah, so
a
it
solid
replaces
copper.
the winding that you would find in an old motor.
And it's like a solid piece rather than
a solid piece
flexible
of
winding.
copper.
Okay.
Now, the tolerances on these are not huge, but actually the geometry of them is difficult to measure, because what you want to actually ascertain is the full profile of that shape. So how close is it to CAD? Now, the problem that you have with that is that there is a design drawing, but because they're bent copper, they are nowhere near the design drawing. So what is your baseline? So you need to first work out, is the simulated shape that you've designed your nominal CAD to the shape you want? And what's more important, is it actually ascertaining that shape, or is it making sure that each one you make is the same? So that's two different things. So what we would do with something like that is take one of our high accuracy machines and laser scan that part. So we would try to reverse engineer the initial master part. And then we can use other tools we've got within the portfolio, things like a P8, which is a tube inspection machine historically. And we can feed that reverse engineered data into it and then very quickly inline capture the parts that are coming off the production line, and then look at them in respect to how they were actually made initially, how they were made to the master part. So that gives us a way to check, first of all, how close are we to nominal, but also how close are we to each part that's produced. So things like that, that's where at the moment we're seeing new applications for things, because as part of a combustion engine, that's not something we've seen before. All right. If we then look at other components in there, like the gearbox assemblies, there's lots of parts there where we already have existing knowledge, but we have to apply that existing knowledge in a different way, because the key points of those components, that what we actually are interested in from them is different from a combustion engine. So that's where we get into conversations about the noise of powertrain and how that applies and what's the best way to handle that. Is it to improve the quality of that product? Is it to make a better gear? Or is there different aspects to the manufacturing process that produce a noise and we're not sure what that is? You know, there's conversations we've had where you have a gear profile. We're already in the order of sort of a 3 micron profile tolerance. So you need the absolute best machines with the absolute best capability you can get to inspect that now. Now, is it viable cost viable to actually improve that process and make a better one, chances are that's going to be quite a costly thing to undertake. And do we know that just making a better gear actually reduces the noise? We don't. So that's where we have to look at, sort of think outside the box and think, is there a noise we can make it produce that actually resolves in something that's actually audibly nice? And do we do that by actually changing how we produce a gear and actually machine in different frequencies to make the patterns we want, rather than try to make it silent? So there's lots of conversations like this, and this is where all three of us here kind of come together through the design and engineering, the simulation of what we expect, through the manufacturing and how we actually produce those shapes and forms that we want, and then from my side, how we actually capture that data and feed it back to validate that, first of all, the simulation is in the realm of what we're expecting, and also that we've produced the part that we expect to produce.
Absolutely. That's absolutely fascinating that you need such a, when you're designing a new product like this, you need, and it's such an integrated approach between what the physical characteristics of it are, if I can say that right, and then what the ride is like, and then what the user experience is, and what the cost is, and there's all these different parameters you need to optimize all at the same time, which sounds kind of almost in my mind impossible. I mean, how can I throw a question out? How do you even go about designing something as complicated as that? Is software the kind of the silver bullet?
Oh, I suppose that's for me, is it?
That one's for you.
Everyone's looked at you, Reece, I'm afraid.
Yes, so how do you go around designing it? So again, I can come at this from a transmission point of view. So the first thing that really you start with is the conceptual layout of the transmission, understanding what your inputs are and what your outputs are. So again, from an electric machine design for what's the input speed of that motor, to what's going on at the output. And then it's a case of how you're going to get from your input to your output in terms of the ratio, overall ratio of speed reduction from input to output, but then also you're not usually going to get that in one gear set, so it's having multiple stages, and then how do you split the ratio between each stage, and then it's got things about layout of the position. Then you're adding more detail into the model, updating the shafts, understanding the features on the shafts that you're going to add. So even sort of just mounting bearings onto a shaft, you might have to have special undercuts that are cut into the shaft. How do they act as stress raisers for the fatigue properties, for the fatigue performance of that part? Then you're looking at the gears, and you're looking at how the whole system interacts and how it deflects, and then how do you design the gear for maximum efficiency, durability, noise requirements? And again, you're trying to. I always say that people say, I'm going to optimize this. There is no such thing as an optimized gear. There's no such thing. It's a compromise, and it's the best compromise of all the characteristics that you're going to have. And then we're feeding all that information into simulation to understand, how it's going to perform, and also, even the link between Romax, which is the tool that I know most about, with Actran, which is our acoustic simulation. You can start to determine how that noise propagates, in a full vehicle model from the transmission within the realms of the bonnet of the car to the occupant's ear.
That was going to be my next question, actually, is how you go from a kind of a maybe even a geometric design of a gear train, powertrain, and a motor system. How would you actually translate what is kind of a set of numbers in a computer is your gearing system, your motor, your input speeds, to what the drive experience is for the person sitting in the car in reality?
Yeah, and it's a real the key part of it is that there's not going to be one tool that's going to be able to give you all the answers, and it's about effective linking of processes and linking of information and sort of co-simulation in some cases between different tools. And we're very fortunate within Hexagon to have a whole dedicated team which work with customers. There are applied solutions team, and they work with customers to link together the processes that you would need to build an EV powertrain or other components as well. And they have the full access to all our design and engineering portfolio to really optimize that process. And we have experts in all various domains that are required within an EV transmission.
Brilliant. So I guess if anyone's listening to this and they're a design engineer in I don't know, maybe a tech startup, and they've not quite got all of that bespoke domain knowledge in that area, then I guess you can start taking on. I've seen a bit more of this of outsourcing some knowledge areas to a specialist company like Hexagon, who know about manufacturing, who know about inspection and metrology. How do you think? Why do you think companies are starting to outsource some of this knowledge to specialist companies? Do you think it's something that is useful for companies? Do you think companies should be making sure that they've got the knowledge in house to be able to do these kind of specialist jobs?
So, one of my colleagues actually has picked up on this over the past couple of years. But we're going to talk about gears here because it's what I spend 90% of my life doing. But we've found, as from the production software side, as machine tools become more capable and the CAD/CAM packages become more capable, that allows companies to venture into industries that before was a specialised group, right? So if you go look back tens of years, you're in a gear industry where there are specific companies who specialise in gear manufacture, and they have dedicated tools to produce those parts. You buy off-the-shelf product to a specification and you design it into your own assembly. The same applied with metrology. You've got dedicated gear checkers, and it was like a world within itself. And over time, as the CAD/CAM packages become more capable and machine tools become more capable and accurate, you're at a position where those companies can now delve into what we would class as special geometry applications and start to produce parts because of the technology and the software behind it. But there's still a specialism within that product range that the people who maybe produce them don't necessarily have a full understanding of. The same applies in the metrology world, where we've got very capable CMMs that can set the standard in gear metrology and modules that can go and measure a gear. But when you get the output from that inspection, how do you interpret it? And you still need
that's the domain knowledge.
Yeah, that's the domain knowledge. And you still need to have the expertise in the gear industry. You can go through the software and populate the information to get the machine to go and make or measure a gear. What do you do with the output? And it's that domain knowledge about the output and the information and how you use that then informs how you can develop it further. So I think that's where we see a lot of what we would put under the consultancy banner, is where there are companies who have delved into these special geometry industries, which doesn't just apply to gears. There's lots of this that now applies across the board. And we find that because we do interact with these parts, we have a level of knowledge that does allow us to take that information back and interpret it and produce that consultancy-led business.
I think as well, on that point that you're making, it's important to say as well, even from a specialist point of view, it's often very difficult to see a measurement report and someone say, okay, how's that going to affect
what's the result going to be?
Performance?
Is it going to be annoying noise? Is it going to be nice noise?
Yeah,
that's very true, actually.
Exactly, and it's kind of what led us to. So from design engineering, we've partnered with metrology to, and especially the Quindos gear measurement software, to link back to Romax software, so that we can make that connection between the manufactured part and the simulation. So allowing us to make that decision of saying, okay, how is this going to affect our durability? How is this going to affect the noise?
Yeah.
We can say, okay, well, give us the data and we can tell you.
It's a very good example, actually, because there's been cases where we've worked together between Romax and metrology, and we've had situations where there's a measurement gone through on a machine on a gear that you have knowledge of, and there was a case where we'd measured the gear and it should have been a high spec gear, and we actually saw error in the output results. Now, based on the experience I have with the metrology side, it was straight away we could discern that error was likely not the gear. It was actually the assembly of the gear to the differential. And what we saw on the output report was effectively a run out, and it was down to how the gear had been bolted to the diff. So we removed the gear from the diff, remeasured it, and then we were in spec, right? And that goes back to exactly what you say, where from your expertise in the gear industry is well above mine, but then my interpretation of the results comes from the experience of understanding
how these
metrology
mechanical objects come
interact.
together,
Yeah.
which doesn't matter whether it's a gear or a mold and die part.
Yeah.
You know how things will bolt together and what errors look like, what underlying problem you've got. And that's where the connection between these two, some might consider separate experiences, actually results in a much more successful kind of project.
And I think as well, it also opens up some really exciting possibilities. And again, linking further within the simulation world of using artificial intelligence, which is obviously a very big buzzword at the moment, which we hear a lot. But people often think, like, how is this actually going to improve life? So from a manufacturing point of view, it's being able to take that data that we've measured and bringing it into the simulation software and getting really quick results. So if you have it's this word, I don't really like the word, but it's true. It's like democratizing that capability. It's giving the ability for someone on the inspection line to take a measurement of a gear or part of the assembly line to say, okay, I've put all this information that I've got into this model. I can simulate what's going on, and I can get a simple green light, red light, amber, to say this part's going to be good or this part's going to cause a problem within my transmission.
And there's also more of a move in metrology to bring inspection from what would be kind of a dedicated inspection room to the shop floor, which is quite hard because it's a difficult environment. It's dusty, it's noisy, it's not a nice environment for precise inspection equipment. And Gareth, because you're into production, making sure that machine shops are making good parts. Where do you find yourself trying to bring inspection in? If you go, let's say, from a site visit or talk to a customer about how they're going to make a part, do you ever try and bring in process inspection into the picture?
Yeah, so again with that, we've got great links with the metrology team as well, but we actually have a product called EdgeCam Inspect. So again, it can work with EdgeCam or it can be a standalone system. So again, this allows your machine tool to measure the part. It's based on PCDMIS technology, which has come from Hexagon, which is renowned and been in the marketplace for many years. And we've now got a new product, and that links to NC Server. So again, the machine tool will measure the part. It will then collect the data. It will then look at what it's supposed to be producing, compare the results. If there's a deviation, it will then feed that back to the machine tool control. It will alter the diameter and the cutting length, and then remachine the parts. So again, you're getting a complete solution. So the idea is you can run your machines lights out and know that when you come in, you're going to have some correct parts. And again, this data also gets fed back into the QDAS and Quindos products as well. So again, that can be passed to the metrology side.
Absolutely. And do you think that with the proliferation of electric vehicle manufacture, there are some specific components in these kinds of vehicles that need that really critical inspection all the way through process, maybe it be heat treatment, roughing, finishing, all those kinds of processes?
Yeah, no, definitely. There's various parts of the process that definitely need inspection on there, like the gearbox. Even electric cars have gearboxes, motor housings, things like that. So need to make sure that the bearing housings are correct. So yeah, it's definitely more important nowadays.
Absolutely. And if someone chooses to, rather than go for optimizing the gear, the gear resonance to make sure it's a noise that sounds good, if they actually try and go for a super precise gear, then they'll definitely have to do a lot of in-process inspection, won't they? But don't go for the super precise gear. Try and make it sound good, right?
Still needs to be very accurate.
Still needs to be very accurate. Sorry, I've just upset a lot of people who make gears. Yeah, I've upset a lot of people in the gear industry right there. Now let's move on. We've been talking a lot about kind of components and and simulation and the kind of nitty gritty. Let's go up a step above and imagine we're all sat in a lovely electric vehicle right now. What is the drive experience like compared to a normal combustion engine? The handling, the noise, what you kind of expect. I mean, we're going to talk about range a lot. The elephant at the bottom of the car again. Yeah. We're going to talk about the range in a bit. But what is the drive experience different to a combustion engine? And how do manufacturers try and optimize those?
So again, I think you already touched on one of them, which is the noise and the driver will experience, and obviously when you had an internal combustion engine, the biggest source of noise would have been the engine.
Yeah, all the explosions happening.
The combustion cycle is going to generate a lot of noise. Without that now, you now are experiencing other noises, and especially within electric machines, you get a lot more high frequency stuff. The stuff that's going to be a bit annoying. I won't make a noise now. Don't worry.
If you go to the back of a machine tool and you hear the hydraulic motors, it's a horrible whine, isn't it?
Exactly. And again, you're getting that from the electric machine excitations on the teeth of the stator. Which translate to the housing and become radiated noise, and also from the gears as well. So now the question is, okay, we don't have this masking noise. How are we going to, we have to have much more control over the sources of noise within the
Can I ask you a really stupid question?
Yeah.
Now this is going to be a really stupid question. Do electric cars, do they have, I mean, there are some electric cars that have kind of four-wheel drive where the motor is placed directly on the wheel-ish. And there are some where there is a kind of a central motor that would have a drivetrain to, let's say, the back wheels.
Yes.
Those two would have very different noise, I guess, profiles, you could say, because you get noise from all around the vehicle if you had four motors.
Exactly. And that's something that's really important as well when we look at vehicle noise with Actran. Again, you can set up a model and have these sort of almost point noise sources within the model and understand the effects of, okay, I've got a noise coming from the center in front of the driver to I've got it at four corners.
What from playing heavy metal through the radio as well? Is that?
I'm sure if I ask the guys there, they can simulate that for you as well.
Simulate a bit of Rammstein. That'd be good.
Yeah.
Fantastic.
I think maybe that's their sort of tagline.
That's their expertise, isn't it?
Rammstein covers all gear noise.
Exactly, perfect. Every frequency. So gear noise is a big important factor. We've talked about gear noise already, about an inspection, about trying to either change the frequencies or the accuracies. But moving on to kind of more general, everyone likes driving a car. Everyone likes driving a car that handles well. What does the construction of the car change the kind of the handling?
And again, I think from a handling point of view, it's going to be a case where the mass is in the car and where it's distributed. You often hear when in the old internal combustion engines, it's got a 50-50 weight distribution or like this. Now it's a question of where it's 50-50 front and back, but what about height as well? Where is its position there? And again, it's tuning the mass of that is now affecting how the ride and handling is going to be affected. So it's going to require tuning of the suspension systems. And again, simulation of that.
And wouldn't that be using Adams, the kind of multi-body simulation? Because
Exactly.
Adams has been around for a long time. It's like a solver, isn't it? That's been...
Yes, I don't know the whole history of Adams, but it's certainly been one of the... been around for a fair few years.
and is that kind of the de facto standard? Is that what most motor companies would be?
Yes, so Adams' car is very much ubiquitous with ride and handling for automotive companies. And it's got many features with it which make it, in terms of like sort of setting up templates of the model, which make it much simpler to analyze.
Okay, so we've talked about what happens when the car's moving. What happens when it stops and you've got to charge it up? And what is and there's kind of two parameters here. There's kind of the speed of charge, how long does it take to charge the car up, and also how much does it cost to charge up as well. I mean, Ollie, you had quite a funny. You did a bit of a Excel spreadsheet, or maybe probably a napkin calculation of how much it would cost you to run. Can you tell the story, please?
Yeah, so it was. I was looking at buying an electric bike, so I wondered how much it would cost.
And how far is your commute, out of interest?
10 miles, not far.
Oh, you're upsetting
Perfect.
everyone here now.
Yeah, it's great. Lying every day.
Lying to 5 to 9.
That's it. So,
and he flies in his personal helicopter.
so I wondered how much it would cost to run, let's just take the 30 days to and from the office. And when you work it out, it's about £1.70. Just
£1.70.
Because you're talking like a 250 watt hour battery, and you're getting because you're
and do you actually have to cycle? I was going to say, do you actually
effort in yourself?
So you need a
aren't you?
Weetabix.
It's just that little bit of help, right?
Yeah.
So
that's why you
you're
didn't have
putting
breakfast today, because you were
effort-
driving
exactly.
today, weren't you?
You're putting a bit of effort in yourself. But when you consider that versus how much energy you're using in an electric car, especially at the current electric price, there's a significant difference from like tens, 20, 30, 40 pounds versus so this goes back to what Reece was saying about the weight, obviously.
Yeah.
So maybe I'm a lot lighter than an electric car.
Maybe you are, yeah, exactly. Well, obviously you need to eat a few more pies. I'll get you some pies at lunch if you want. But like you say, it could be 20 times more expensive to run an electric car versus an electric bike. Why is that? Can I ask an open question? Why is it so expensive?
I think the simple thing, let's not make this too much of a physics lesson, but Newton's law, force equals mass times acceleration. So when you've got a vehicle and you're accelerating it, or when you're accelerating it, obviously you have to brake at some point. That is going to expend energy or force and energy, and so the heavier something is, the more energy it's going to use to accelerate up. So yeah, that's obviously why you require a much smaller battery and a much smaller motor within an electric bike than a car.
I guess that makes sense because a car is kind of almost 20 times the weight of a bike.
And the rest.
And more as well, I guess.
Yes, I don't buy heavy bikes.
Do you not? No, well, okay, all right, fair enough. I'm with my 90 quid steel bike, carbon fibre.
Yeah.
All right.
But yeah, and I think it's a decision that's been made within the automotive industry, especially in the early days. We are still in the early days of electric vehicle adoption, even though it is increasing very quickly. Which is that to make it worthwhile to them, they need to make it a premium product. Premium products are big and they're heavy. So essentially now the trend is to have SUV type. SUV type electric vehicles,
which are like what, a ton and a half,
2.5 tons.
Oh my god, that's way more than 20 times the weight of a bike. I misestimated that a little bit, I think.
And then you see decisions, again that recently of Ford discontinuing the Fiesta because it's not a viable electric vehicle, and their plan is to go to electric
Shame, because I
vehicles.
love my Fiesta.
Yeah, I think everyone must have owned a Fiesta at some point.
Absolutely, great vehicles. No, Gareth's shaking his head. No, Gareth had a Porsche for his first car. Yeah. Is it McLaren?
In my dreams.
Absolutely. And when it comes to kind of the weight of the car and the that's taken us to the range and the cost of charging it up. What do you think the options are for keeping the same premium feel for a car versus my Fiesta, obviously, which is certainly not. I'm not going to go there, actually. What do you think their options are for different materials, more kind of futuristic, composite-y type materials in kind of the chassis and the critical components of a vehicle that might improve that weight and that range?
So I think obviously the one that springs to mind first off when you talk about exotic materials are composites, carbon fibre, and that, where you've got a sort of fibre inside a matrix within the vehicle, and obviously they can have really good benefits that can be tuned based on the layup of the fibres and various construction of them. And again, linking back to Hexagon and what we can do, we have a great product called Digimat, which can analyse those composites. And I suppose the big downside of them a lot of the time is that you're not always 100% sure how they're going to fail. So when you're designing something, you might add a factor of safety into that design because you haven't got that confidence, and simulation tools like Digimat, which can model those fibres and really go into detail on how they're constructed, allow designers to be a bit more bold with how they're designing and really get those weight savings that you're alluding to into the cars, and again bring down the overall mass of the vehicles, which inevitably will result in cars that can that will achieve higher and higher ranges.
I'll just jump in there as well, because obviously you're talking about the carbon fibre and the layup of that and how that impacts strength and weight. So it's not my area of expertise, but again, on the metrology side, there are sensors that are available. So I think it's called the Apodia sensor as part of Hexagon, which is actually a sensor that is there to inspect that layup. So if you've got the design of the layup, you can then validate that layup has been produced in accordance to the spec that was set. So that's where we're looking at, there's the different technologies available there, that if you've got an aluminium chassis, it would usually be on a large, maybe twin arm CMM or something like that. If you're in the case of a monocoque carbon fibre chassis, okay, you still got the dimensional aspect to that, which would still be probably on a CMM. Probably something like a Global or something like that.
But you've got that integrity of the
additional
material
sensor now that you can add to these systems, where you've got that, you're looking at the actual material integrity, like you say.
Mm. And also as well, you link to sort of the volume graphics side of CT scanning, I guess, can also understand as well.
Can I ask you what CT stands for, Reese?
Again, this is me outside of my area. Let's see. I actually asked this question earlier.
I'm only joking. Sorry I put you on the spot there.
That's the problem of using an acronym when you don't understand them. But what I do understand is that obviously, again, you can use to look at the layup, but then also its question is, are there air pockets that have somehow got in between the layers? Is the fibre sort of connected completely to the matrix? And again, using the CT scanning and volume graphics, you can effectively look inside the structure and understand how homogeneous or non-homogeneous it is, as it would be.
It's an interesting point because the range bit, obviously there's the weight aspect to it, but then we've also got the how efficient are all of the components together, because obviously everything moving is just going to waste energy. So you've then got, you look at the portfolio from a metrology aspect and how that impacts, let's say, range here. You've got the body panels. So how aerodynamic is the car? How slippy is it through space? That's going to have an impact. So in that sense, if you're looking at the panels, you're looking at the design and the lines of the car and how the air flows over them. As part of the simulation there, we'd be capturing that surface data of the body panels using maybe an automation cell using a robotic arm and a laser scanner that's connected to a tracker. So for the large volume metrology, as we would class it, where you're actually capturing full surface data of those panels to then perform maybe the simulation on how the car actually performs,
rather than
what
the CAD model looks like.
Exactly. Going back to the gearboxes, how efficient that drivetrain is on the data we've collected from those gears. We pass that back to Romax, and then they can perform a simulation with the actual gear mesh rather than the simulated gear mesh. What are the efficiency losses there? So a lot of the work we do now is we've still got our everyday metrology tasks in the sort of general metrology as people think about it. We measure things. But then we're looking at it with the new sensors that Hexagon develop all the time, which is a big part of what Hexagon as the metrology arm does, development of sensors. How can we take new sensors and how can we apply them to applications to gain data that we've not had before, that we can use to maybe find things that we didn't know or we knew about but didn't understand.
Yeah, in the same way that you came in to the gear that was not inspecting correctly and you had that weird bit of domain knowledge where you knew that you were just bolting it wrong, there might be some piece of information that you're just missing to explain some weird phenomena that you can't explain. You're having to scrap 1 in 100 just for whatever reason.
If you take any inspection at the moment, it's normally a sampled inspection. You're taking discrete points or discrete scans across a surface, and we're assuming that the coverage we've collected contains the information that's relevant.
Representative sample.
A good example of this is some of the work we've done with Romax, where we have standards that we apply to a measurement, and that is the way we validate the part, and it's the way we should validate the part, and it's actually a very good method of validating the part. However, if we're looking for those small gains and trying to understand how things perform, is that data enough data? Is it viable? So we're trying to find the balance between what we can collect in metrology, and we trade off speed versus accuracy all the time, and what we can give to Romax. So in this example, you're taking a gear and you're doing your standard gear inspection, which is the valid way to do it, has been done for a long time, and is incredibly accurate. That doesn't give us a huge amount of surface data to supply to Romax. So then we can potentially pick up a laser, or I say potentially, we do. We can pick up a laser scanner and scan that gear. But now we've got a problem where we've got gear data that's collected using a valid, approved method that we can trust and share around the country with lots of different national labs and prove that the method works. We've then got a data set that's the full gear as a point cloud with millions of points, which is could be really useful. But how do we validate that the data from the laser scanner, which is inherently less accurate than the traditional method we use, is going to give us the right information? So one of the ways we do that at the moment is we actually we can use both in combination. So on our lights product range, we've got a system called Semmation, which allows us to take a CMM and specify multiple different sensors on it. Okay, so I think we had an event a couple of weeks back and a few of you came around and saw this. I think you actually saw the exact application I'm talking about here, where we measured the gear tooth the traditional way and we get an evaluation for it that we can validate and trust. And we then collected the laser scan. And because we're using one system with a set calibration with the same reference point and the same software, we can then correlate those two methods together. And at that point, we can look at, we can understand the level of uncertainty between the two. and we can correlate them together. And if the correlation passes an acceptable limit, we can then pass that point cloud data, the full surface data, the full topographic data, back to Romax. And then they have a full surface model that they can do work with, rather than creating a parametric model from
that just fits those points.
So this is sort of the work at the moment where it's not standard metrology. It's not what we do day in, day out to pass off parts. It's looking at how we develop metrology, simulation and production for the future as well.
Absolutely. And it's funny you're using kind of a bit of a statistical, not trick, but a statistical correlation to make sure that point
We're using
right.
what we know to understand what we don't know.
Absolutely. And how... Okay. That's fantastic. On that, I think on that note, that's a fantastic way to move on. And we can move on, I think, probably to... we're going to speak a little bit about what I think is very important to everyone. It's the environment. It's where we live. And that's why we're talking about EV cars today, is because what the effect combustion engines have on the environment. But what I find interesting is the materials used in an EV car are all very, like you say the word, exotic, aren't they, Reese? Compared to a combustion engine, it's kind of steel and plastic and aluminium for the engine block normally. So what materials do EV cars use, and are these sustainable?
I mean, it's a very much a hot topic at the moment, and something that's got a lot, quite rightly, it's got a lot of coverage about things like within the battery, the lithium mining of and nickel required in the battery, but then also within electric motors. I mean the current de facto electric motor will have rare earth magnets within them, and within Romax in our research and development team, we have been doing research projects over a number of years looking at novel motor designs that can eliminate those rare earth magnets. And I know that there are other companies around the world that are also doing similarly sort of. And again, we talk as well as the environment. We're talking about supply chain issues at the moment, which are affecting a lot of the EV manufacturers. And again, being able to broaden the sourcing of those materials or eliminate them from your sort of supply chain should, again, speed up that time to market. It's not uncommon to hear people talking about 12, 16-month waits for an EV car because just struggling to get hold of these parts after the pandemic and us ramping up and this new almost paradigm shift in terms of what we want for future automotive.
Absolutely. And I think that's probably the dream, is to make a clean vehicle that doesn't emit anything, but with simple materials, not with these complicated lithium, nickel, heavy metals that can again damage the environment. Shall we move on a little bit to, I think, Gareth, were you the one who mentioned that EV is not the only option? Yes,
there's also hybrid. So again, using conventional petrol engine with an electric motor. So that's personally what I'm driving at the moment. And yeah, it seems to be good. And again, I'm finding with the location of where I'm living, there's just not the infrastructure in the UK to support electric vehicles. Typical example, I stayed at a big, well-known hotel chain last night. 2 charging points.
For the whole hotel?
The whole hotel. So, and this is probably 5 miles away from where we are today. So,
and obviously MTD studios in the centre of the world, so that is ridiculous.
Yeah, of course.
Absolutely ridiculous.
Everything revolves around there. So.
Yeah, absolutely. We wish anyway.
Yeah.
It's a really good point. Is infrastructure? I mean, we could probably spend an hour talking about infrastructure as well, and what is required to spread the adoption of EV even more. Thank you very much, Gareth. And I'm going to finish on one last point, because I'm sure everyone is ready to have a good glass of water now. Is Gareth? You've said you've got a hybrid.
Yep.
Has anyone here actually got an electric car?
Unfortunately, not.
No. No, you're not, Ollie?
No.
Unfortunately, I've got my old Fiesta still, my dirty diesel, unfortunately, which is it's going to be a relic soon. I'll be able to sell it for a lot of money, it seems. I'll be going to Tenerife next year. You'll get a photo from me. So, unfortunately, the 4 people around the table, quick survey, don't have an electric car yet, which shows that still the adoption is not quite there, unfortunately. I'm going to extend it. We've got Paul and Vicky and Lindsay in the studio. Have you guys got electric cars? Yes, Vicky's got one. Yeah,
I know other colleagues who are waiting, and I'm interested to see how they get on.
It's getting delayed.
Does it keep so your car is delayed? So Vicky says she's got one on order.
At the moment, and I've got one.
She's on the hybrid, but your electric is delayed. Do you know how long it's going to take?
It was supposed to be February. It's been pushed back to March.
So it was supposed to be February. It's pushed back to March, which is, I mean, it's hard to adopt one if you can't even buy one, can you? No matter how, for love nor money, unfortunately. But that's been the MTD podcast. I hope you guys have learned. I mean, I've personally learned a hell of a lot about the manufacture of electric vehicles and about Hexagon software. I didn't realise you guys were in so many different areas. And thank you very much for all of your topics. Has anyone got any final comments?
Well, I don't know. I think I touched on this earlier, and maybe I should point at this point say this is a personal opinion. And
I'm going to say Reece has very controversial opinions about electric vehicles, apparently.
Oh, as I said, it makes it sound like I'm going to say they're rubbish and no one should have an electric vehicle.
Of course not.
But I think there is. I think the future mix of transport needs to include both what we see at the moment, sort of in the marketplace, but also other forms of short distance mobility. So you talk about electric bikes and smaller battery sized EV vehicles with fewer seats. And I think there's a real gap in the market at the moment for EVs.
When's your new startup coming out?
Well,
I'll be the first to invest. I'll give you £1. Okay, that's been the MTD podcast. Thank you very much for listening. If you've got any comments or you want to ask any questions from any of our panelists here today, then please get in touch on all the social media, either at Hexagon or MTDCNC. Thank you very much for listening, and make sure you subscribe. Cool.
Thanks for listening to the MTD podcast. If you found value in this episode, please subscribe and leave a rating and review. Find more episodes on mtdcnc.com.